So the topic for today, it's a new topic. It is clustering. And we will learn about a class of algorithms that are called clusterers. This is a large family of algorithms, very much like regression and classification. They're large families of algorithms, and every time newer and newer methods are being found to do to do classification and regression. In the same way, the world of clustering is large and vast, but it is a shift away from making predictions. So far, our machine learning exercise has been to predict something. From today, we will focus not on prediction, but on pattern recognition. We are looking for certain patterns in the data. So there would be nothing to predict. There would be no target variable. We would just look at the data, the entire feature space of the data, and ask, what is it that we are seeing in it? Is there a pattern to this? Right? Are there something interesting things? Is there something interesting going on in the data that we can discern? And that is the topic. Usually this pattern recognition is called, unsupervised learning. Whereas the predictive modeling that we were doing, building classification models, classifiers and regressors, those are called supervised learning methods. So the machine learning community has been pretty divided into two, not community, sorry. The subject has often been split into two sub-areas, that of supervised learning, so-called, and unsupervised learning. These words are old words. And in some sense, I'm not very fond of these words. I prefer using the word predictive modeling and pattern recognition. Part of the reason is we now have classes of algorithms which are hard to, in a very clear-cut way, say that they are supervised learning or unsupervised learning. We have the world of semi-supervised learning. We have the world of self-supervised learning. And so this word of supervised and unsupervised learning has gotten a bit complicated. There's more and more things to it. And sometimes there's disagreement on what to call it, right? Or how to think about that. So we will use more explicit terms like predictive models, recommenders, dimensionality reductions, clusterings, pattern recognition topics, and so on and so forth. So today we are going to talk about that. What are the topics that we will do? We'll, as usual, review, give half an hour to reviewing. What is it that we learned last week? Now, in this case, it wouldn't be last week. It would be what we learned this Tuesday. In case you missed Tuesday, I would encourage you to go watch the video. We covered an important topic, discriminant analysis. So that we'll review that. Then we'll start with the world of clustering. I'll explain what that means. And we'll start with the simplest of all clustering algorithms, perhaps, the k-means clustering, which we will do in considerable detail today. Time permitting, we will also do agglomerative clustering and some aspects of it, like linkage and so forth. Then finally, we will look at what are some of the limitations. As we do these algorithms, we see they are very effective. They do work quite often. And in fact, these are the workhorses of the industry. Whenever people think of clustering, very, very often they think of k-means clustering or hierarchical clustering, agglomerative clustering. But these things do have limitations, which is why there are other algorithms that we'll cover next week. Those are density-based algorithms, and if time permits, a few more. Now, in the lab, we are going to do three things. First is we will do the Wisconsin breast cancer data set. This would be a practical walkthrough, a data set that has been of significance for many years. It goes to the heart of this endeavor within machine learning community, within AI, to be of value to the medical community, to be of value in the diagnostics. It is, at this moment, we are talking 2021, end of 2021, we have mixed success. In many places, it is a good assist tool for diagnostics. In many other cases, it could do better. We are not there yet. For example, for COVID-19 detection from X-rays and for COVID-19 detection, the AI, there is a report that says that the many approaches were tried in AI, but actually it did not succeed. It did not. They all had enough success, but not good enough success to replace or to be deployed in the field at large scale. That just shows that the state of the art leaves scope for improvement. And here also, we will talk about the breast cancer data set. I'll give you a little bit of a background. It's a simpler data set than the COVID data set, COVID X-ray data set. The COVID X-ray data set will do, or one of the data sets, we will investigate it in the next workshop, but because that needs processing of large image files, and building models over them, it needs deep neural network and things like that. So we won't be having that here. So today we'll start with something simple, the Wisconsin breast cancer dataset. While we are doing it, I will also take the time to introduce something that is Holt, one of the people involved in the Wake Up project, I believe. Not Holt. Okay, so one of the people made an interesting breakthrough. They pointed out that sometimes very simple algorithms yield results very close to the state of the art. So we are often fond of new tools. Remember, I talked about the photographer. We all get into photography, and the first thing we do is buy big lenses and the state of the art, DSLR bodies. But as you know, great photography is done by people who are not necessarily using the shiniest toys, but who are skilled in the art. In a similar strain, there's an observation in the field that quite often, in many situations, actually you come very close to the state of the art by using very simple models, surprisingly simple models. You wouldn't have expected them to work. And therefore, there's a word of caution or an encouragement. Start simple. Don't ignore the simple because there are shinier toys around. So we'll learn that lesson. Finally, I'll take a detour. You all have been seeing some data visualizations. They're all the standard bar plots and box plots and so on and so forth. Now, visualization, as I said, is where art and computations meet. Science and art meets, engineering and art meets, or whichever way you say. The STEM field and creative arts meet. And people have created hauntingly beautiful visualizations. Today, we will start with a very simple visualization, which I would consider, which has been very important. And we'll go through it and see how step by step you can build what looks like a complicated visualization, and you can sort of build it step by step. We will take, in fact, Florence Nightingale's classic 2 Roses visualization, which had such a profound effect in the world historically. In fact, it is a visualization that practically started the modern practice of nursing. It helped convince England, the Queen of England, and the people that we do need modern nursing practices that we have today. Now, that is sort of the holy grail in our world of data science, to create a notebook, to create a visualization, to tell a story with data that can change the world. Would you not like to do that? Right? And this is often overlooked. If you look at engineers, they tend to create very complex results. They say a lot, but they often end up saying it in very arcane terms that only other engineers can understand. A lot of technical jargon. Visualization, in a way, cuts through all of that and makes what you find accessible as a story to a broader audience. Right? It helps you communicate with not only with other data scientists effectively, but with a larger audience. It helps you tell a story with data to a much larger audience. So visualization I would say, is very, very important. Today will take us a pause from just doing algorithms and notebooks, data analysis around that, and take a very simple data set, I believe just 24 rows or so, and create a visualization around it. So that is the scope for today. So with that out of the way, I would like to now get onto the topic of clustering. I will pause for a moment. If anybody wants to get tea or coffee, please go ahead and get it, and then we will start imminently. Any questions before I start from what we have learned so far?
So then I had a question on LDA. So is it possible to briefly explain the LDA concept again?
We are going to review. Oh, yes, we are going to review that today. So we will do that. Any other questions, guys? Again, may I urge you to take your quizzes and do your projects and your labs, so homeworks. Do the homeworks. Otherwise, without practice, nothing will sink in. Without repetition, without practice, nothing will sink in. Quizzes helps you repeat what you learned. It makes you go back to the videos, back to the textbooks to go find answers, right? How many of you go back to the videos and the textbook to find answers? Most of you do, right? So it is the nature of learning. You can't understand everything the first time you hear it, the first time you understand, but you forget very quickly. But when you go back and review it, that's when it sinks in, when it settles down. Quizzes are important. Likewise, practice is very important. Obviously, you guys are very mature people. I'm stating the obvious. It's almost pointless to do that.
Hard to teach old dog tricks.
That you guys are not by any means old dogs. Sachin is filled with dog metaphors. He has a new dog.
Dogs for sure, not old.
Yeah. Yeah. All right. So where are we? We talked about dimensionality reduction. The discriminant analysis, quadratic and linear discriminant analysis. What we talked about last time is, if you go back to the example that I keep using of cows and ducks, you project them into the feature space. If you look at the data, what you see is, if the x-axis, the horizontal axis is the weight, and the vertical axis is the volume, so these are the x1, x2 of your data set, most of the ducks are small and light. So they will be clustered around the bottom left-hand corner where you see the ducks. Right? And most of the cows would be clustered around the top. Those blue dots at the top right-hand corner are the cows. They're big and heavy creatures. And so the center of gravity, the center of mass, if you want to think of it, of the data points, which is the mean of that two-dimensional mean vector of the ducks and the two-dimensional mean vector of the cows, or more intuitively, the center of gravity points of the two, they would be separated, right? And what you find is that if you think of the weight, the data points, the concentration, their density plots, the probability density plots, it would, the marginal distribution would look like the yellow lines that I have drawn along the horizontal and vertical axis, right? Sort of the marginal, like along those axes, they would look like bell curves, right? So this is it. And the two-dimensional distribution is, of course, like a bell hill. These are called normal distributions or Gaussian distributions. Or just to be more descriptive, I call them bell-shaped hills. Well, no, except that the bell need not be round, it can be elliptical, right? There's no reason why variance in one direction and the variance in the other direction would be the same. Now, with that being there, it almost invites us to connect the two centers, the center of the cow and the center of gravity of the ducks. And then once you have joined it with a line, and that is the dashed line here, then draw a perpendicular bisector of the two. When you do a perpendicular bisector, it becomes a very natural decision boundary. When you do this, and this sort of approach is called discriminant analysis. Here we have built a linear decision boundary. Now I'll show you there's a variant of it where the decision boundary can be quadratic or nonlinear. But to get the intuition right, this is it. But when you do that, we also realize that, see, this axis, the line connecting these two center of gravities, if you consider it as one axis, the first axis, new axis, and perpendicular to it along the decision boundary as the second axis, right? You end up with a new coordinate system, isn't it? We have a new coordinate system. And in this new coordinate system, any point can be represented either in the original coordinate system of x1, x2, or in the new coordinate system of which I've marked in red and I've written as x1 tilde, x2 tilde. Isn't it? This is basic geometry. A point can be written in two different reference frames, so two different coordinate systems. It is the same point, and one is the transformation of the other. One is some form of rotation of the other, or rotation and translation of the other. Right? In other words, it's a simple, yeah, it is a simple translation. Exactly, rotation plus translation. Right? So as such, we are not doing anything magical, but then we observe something interesting. We may argue that if we want to distinguish between cows and ducks, perhaps the only thing that matters is, or the majority of what matters is where the point is on the x1 tilde axis, along the axis of the line joining the two centers of gravity. It is just stands to reason. And we may, to the first approximation, we may choose to ignore the x2 axis altogether. And that is the second beautiful insight from that. So what we say is that by looking at data like this, we get two things out of it. We get a classifier, because by joining this line and doing a perpendicular bisector, we have a classifier. Now we can classify cows and ducks in a very intuitive manner, geometrically, very obvious manner. Do we agree? And at the same time, we get dimensionality reduction. We can say, hey, you know what? In the new coordinate system, let's forget about x2. We can write a classifier in only one dimension, just x1 tilde. Right? So for example, here it would be whether x1 tilde is negative or positive. If it is positive, it's a cow. If it is negative, it's a duck. Does that make sense? Right? In other words, if it is any point here is its x1 tilde value would be negative. Any point here, its x1 tilde value would be positive. And so you can say, you know what, how much easier can it get? Yeah? We have a lovely dimensionality reduction and a classifier that can actually work in lower dimensions with much less features, right? So that is the beauty of it, which is why discriminant analysis is often quoted both as a classifier and as a dimensionality reduction technique. Go ahead, Premjit.
So see, keeping the current context, right? In this current context, the variance is the same for both the distributions. That's an implicit assumption we made. And we took a two-dimensional categorization, which is, or characterization. We had an x1 and x2. And we used just one dimension to be able to differentiate, because
Yes.
after the transformation, there's a positive and a negative.
That
so
is right.
becomes the one qualifying dimension on which we know the value, we're able to classify.
That is true.
Let's say it's a higher dimensionality problem. Let's say there were 3 or 4 dimensions. Then how do you generalize that?
So what happens is, and we'll come to that, dimensionality reduction is a big topic, but so I will deal with it separately. We have a whole day for it, but just to give you a preview, this generalizes well. So for example, let's take the ducks.
Had 3 features.
Some third feature.
Yeah, we took
let us say,
and we took size.
Right. So let me take this. How high can you fly? Right. So the cows can't fly much as far as we know. So there on the z-axis, they'll be sitting down there, right? And ducks, the maximum they can fly will be pretty far up. So now we have introduced a third dimension. But nonetheless, you realize that your data has just become ellipsoidal. It is an egg now. It is not an ellipse, but it's an egg shaped, right? Ellipsoidal. Nonetheless, they do have centers of gravity, center of mass of the data points. And so you can connect these two and still split, right? And you can get your classifier out of that. Now, the second question, therefore, that comes is, what about the dimensionality reduction part? See, when the data is so well separated, right? Dimensionality reduction will reduce it down to very low dimensions. Maybe just the X1 axis will contain most of the information. Trouble comes because reality often is not so well like Gaussian distributions. Like for example, when we go back and look at what was it, blueberries and cherries, they were not Gaussian, they were skewed distributions, if you remember from your Jupyter notebooks, data science notebooks. And so is dimensionality reduction valid, or do you still achieve it? What happens is that you would say that your dimensionality reduction is, always lossy, but the loss of information is significant, right? It is not as effective in that situation as it would be in this situation. So it is a case by case basis. And as always, there is a data rules, right? Data will guide you on how far your hypothesis works. Remember that when you have data, anytime you try any technique, we are building a hypothesis that this technique will work because I believe data is like this. Before you try out LDA, in your mind, you have to have a hypothesis that let us assume that the data is separated out. Therefore, I can do and separate it out, hopefully in nice Gaussian shapes, right? Now, that's an idealized expectation. That may or may not hold. But the question is, what is the level of degradation from that hypothesis, from the idealized hypothesis? And that will be the measure of success of your model, right? Whether LDA works or doesn't work, right, will be measured by how much the data, how much fidelity data has to your hypothesis in that way. And that's the right way to look at it. Remember that given a data, in effect, all reasonable hypotheses are equally valid. You haven't done anything with the data yet, right? You haven't seen it a priori. So you could try each hypothesis represents a different approach. One thinks in terms of logistic, one thinks in terms of LDA, one will do this. Well, many different hypotheses. Every algorithm has a worldview that the data looks like this. And if it looks like this, then it will be very successful. But if it doesn't look like this, there's a graceful degradation. Then there'll be partial success. So you don't know. And in fact, this is one of the things we will talk about in a coming lecture. One of the big themes is, I'll give you a preview of it. It is actually called the no free lunch theorem, or theorems, because there are many of them. Now, the no free lunch theorems are it seems it goes back to there's a bit of a history to it. With the no free lunch sounds almost like a joke or a frivolous name for a landmark or an important theorem in machine learning. But okay, let me take 5 minutes, since this question was raised, to introduce the no free lunch theorem. I'll talk about it just briefly.
So you jump in and just qualify that thing that I asked a little. When you chose the third dimension with the ability to fly, that still gave a Boolean kind of a situation, because a cow can't fly, the duck can fly.
Well, let's add some wings to the cow. Pegasus.
No, I was kind of giving it now, just to keep the example going, yeah. Right? Stretch it. Let's keep it shades of gray. How gray is the thing?
Let me address that. I got your point. I'll address
it's fully that. There, which means cows can be dark, cows can be light, ducks also can be light, ducks also can be dark. So that particular variable does not have any qualifying useful information.
That is true. Then
so
that
ellipsoid,
yeah. So that dimension
on that
that is right. So that dimension essentially is rendered useless. And in fact, one of the great virtues of dimensionality reduction and machine learning is your ability to discern what matters and what doesn't matter, right? And we will learn about that. We will learn about that. Also, the other thing that you alluded to is the fact that we are talking of ducks. But what if you are talking not cows and ducks, but ducks and geese? And now there'll be overlap in weight and size, right? So these two Gaussians overlap, but their centers still exist, and you have still the perpendicular bisector. But what will happen is there would be error rates. In this situation that you look is idealized. You practically think there is no error here. It's very, very hard to confuse a duck with a cow, but it is far easier to confuse a duck with a geese, with a goose, right? Because there is overlap. And so there's inherent error. Because if you do the perpendicular bisector, some of the geese will become classified as ducks, and some of the heavy ducks will get classified as geese, right? So that brings in the error aspect of it, because the two Gaussians sort of overlap, right?
So why does it have to be a Gaussian? You keep referring to it as, why can't it have some other?
Oh, because nature loves Gaussians and we love Gaussians. Gaussians are lovely mathematical functions, easy to differentiate, do many things with. No, okay, simply because in nature Gaussians are all over the place.
No, but what you're saying applies to other distributions.
Yes, yes.
as well.
See, to your point, the point that he is raising is that why Gaussians? It turns out that Gaussians appear rather ubiquitously in nature. And not only Gaussians, there is actually a deep paper. There's a paper actually whose title is provocative. It says, are normal distributions normal? So it asks this question, anytime you see a bell curve, do you just assume that it is a Gaussian? And it questions that, because there's a whole class of distributions in the exponential family that look visually, without doing any mathematical analysis, that look like a bell curve. Right? For example, a log normal distribution can mimic a Gaussian. You can't tell. But then you can make beta functions and other things and Laplace, and there are many distributions that you can make to sort of mimic or be close to the Gaussian distributions, the student T function and so on and so forth. So this student T distribution. The point is that, see, in machine learning, you make a hypothesis that is approximately correct. So you just make the Gaussian sort of stand in for itself and many of the things that look like it. Because ultimately, the goal is not to be correct, which you don't know where the data come from, but to build effective models. Right? So because of that, now the question comes, what if the data is not Gaussian? Like, for example, we looked at our blueberry and our cherries. Truly the data is not Gaussian. It has a strong skew. One has a right skew, one has a left skew, right? Then what happens? Why are we using Gaussians? What happens is that using a Gaussian approach, as we saw in the lab, you saw that even for that situation, classifier 1, LDA worked. You ask yourself, why did it work? LDA makes a Gaussian assumption. The point is that the reason it works is machine learning. It's one of these interesting things I've thought a lot about. See, Gaussian is not it, but it isn't too far from it, right? And because the gradient descent optimization takes place, or any optimization that it takes place, will ultimately say which is the best Gaussian I can fit to this data. And the best Gaussian that will fit in will be a good stand-in proxies for whatever the skew, in spite of the skew in the distribution and the non-Gaussian nature, still it works, right? And this is one of the amazing miracles of mathematics that I find, that sometimes you don't have to shoot straight at the target, just shoot somewhere near, and still works, right? And that is why, and Gaussians are, the tooling is there, everything is there. More than that, Gaussian, see, there is something, there are things like the center limit theorem and so forth in statistics, which basically say when the causes are additive, you tend to produce Gaussian distributions. Like, for example, when you we did that Galton's thing, right, with the rods there and marbles or little sand falling down. It naturally formed a Gaussian because at each place in the rod, it could go this way or this way. So there are additive effects from this, right? Additive effects and lots of additive effects lead to bell curve distribution. And we see that all over the place, right? So what would be your height based on your genetic height? The deviations would be based on so many additive factors, right? How well you listen to your mom and ate food as opposed to eat junk food, right? How well your mom was taken care of during her gestation period. I mean, God knows how many factors, how the weather was, who knows what are all the factors that lead to the deviation from your canonical genetic height that it should be. Those factors are additive, they're independent of each other. Now, sometimes what happens is factors are multiplicative, right? The effects are produced when you multiply factors. For example, the force of gravitation is a product of the mass of the two masses, right? So there are many situations with forces where the factors that you haven't accounted, they're multiplicative, you just don't know them. Generally, when you have multiplicative factors in nature, you tend to see log normal distribution. In other words, remember, log converts a multiplication to a addition. And those additive would be a bell curve. And so the original distribution, if you see a log normal distribution, often you should, and this is, now we're taking a detour and I'm telling you some of the things you learn from the underlying mathematics. And I don't know how much you remember it, but when you see log normal, look for multiplicative factors. When you see bell curve, think of additive factors. It's just a basic common intuition. In nature, there are many additive factors that keep happening all the time. So bell curves are very common. Errors are often additive. You can say that there is a canonical weight that a duck should be, and a volume size that a duck should be. And so every other, a duck being something else, is essentially nature's error. Right, and so it has that's one way to think about it. Not actually correct way, but so biologists will absolutely frown upon it. But you can say, well, there you go. Right, that's the build intuition, guys. See, in this field, right, getting intuition is far more important than for that intuition to be absolutely rigorously true. Right, so go with that. So anyway, I was going to talk about the no free lunch theorem. I'll just stay brief on it. We'll talk about it in great detail in a whole session. No free lunch is exactly what I said. See, whenever you have a data and you know nothing about the data, you can make all sorts of hypotheses. You can hypothesize that it is made up of bell curves that are separated out. You can hypothesize it is made up of a mixture of bell curves. Actually, I'm using bell curve because bell curves are one-dimensional. It's easy to get intuition, but generalize it to higher dimensions. When you do that, those are normal distributions or Gaussian distributions, the bell hills. Yeah. And it's pretty hard to imagine higher dimensional bell hills, but imagine that, right? Like I told you, the mathematical trick is imagine in lower dimensions, but when you speak, say, as it is obvious in n dimensions, right? And you'll be pretty much right.
Hey, Asif, to fit the Gaussians to the data, would you use something like a KL divergence or something like that?
You are getting to an interesting point. Yes, we could. Rantik's question is, can we, this is you, isn't it?
Yeah.
So the question is, how do you know that a distribution is, we made an assumption is Gaussian. How do you know that underlying reality is that? So one way you can do it is, there are these measures, statistical measures, very beautiful measures. One of them is a KL divergence. KL divergence says the data has a certain distribution, you have a certain, but your hypothesis is the Gaussian. How surprised are you to find that it is not a Gaussian, right? Or in other words, how much does the actual underlying distribution differ from the Gaussian distribution, right? And so we, KL divergence is one measure, and that topic is broad. We talk now, I mean, we get into even more interesting areas of transport theory and so forth, but let's keep that for deep learning.
So, Asif, what about the JS divergence?
It's the same thing. JS is a symmetric version of KL.
Oh, okay.
Yeah, but let's not bring those words. See, one reason I'm hesitant to bring those words is because we have people, obviously the people who are learning this for the first time, Rankit, that includes you. And
Wondering, where did he pick up?
no, because he is also doing a project with me with that. So at this moment, in the interest of people who are learning for the first time, let's just not bring in that machinery. But since you brought it up, that's your answer. Does that answer your question?
Yeah, that suffices. Yeah, thank you.
Yes, and the earth mover is the transportation problem, or
Was that?
the earth mover distance, is that the transportation problem? You mentioned.
Yeah. Oh, yeah, it's essentially. Yeah. Okay, see, here's the thing. Now we are getting into the territory that is the engineering math, the math of data science. Let's keep it today. I have a lot to cover, guys. I have a lot to cover. By the way, the interest list for how many of you are enrolling for the math of data science, that list contains just 1 or 2 people. Remember that my minimum quorum is 15, right? See, here's the thing, guys. There is for this business. Okay, so Kyle, please stop the recording. So the no free lunch theorem states this, a very obvious fact. Theorems, actually, they're theorems. So they say things in a technical and very precise language, and they represent one of the most profound discoveries in the theory of human knowledge, actually. From the field of computer science, we have not made too many advancements to the fundamental theory of knowledge itself. Right? Like I'm talking about big milestones, like, for example, Gödel's incompleteness theorem, which says that no body of knowledge will ever be complete, right? And things like that, profound statements, proven mathematical statements. So things like that we haven't contributed. But there is one contribution that came out, and it is very surprising. People in computer science, not many of them are fully aware of it, is the no free lunch theorems. Very profound. It is a revolution beyond just computer science. It states that given many theories, many hypotheses, in general, no one algorithm, or hypothesis or algorithms, no one algorithms will always outdo another algorithm. So these days, you must be hearing fancy statements that, oh my God, we have, see, every generation, and I've been in this journey for a long time. It used to not be called what we call it, all of these words now. When I was in grad school, we used to call it, well, we did a lot of numerical analysis, and we did a lot of modeling, and we just called it modeling and model building and numerical analysis and so on and so forth. And obviously the subject has been evolving since then, and we did machine learning gradually. So over the years, many generations of algorithms have come that have become the fad. And people have said that if you have that, you don't need to learn anything else. It was true about decision trees. There was an algorithm called decision trees, which you'll learn shortly in a couple of weeks. And people said, once you know decision trees, it can do regression, it can do classification, and so on and so forth. You don't need to learn anything else. Machine learning ultimately boils down to gossip plus decision trees, right? There are people who seriously said that. And so decision trees, people came up with faster and faster implementations of decision trees. It was an industry. Today, we know that's not strictly true. Nobody in his right mind in 2021 would say that all of machine learning comes down to decision trees. But then came, for example, the kernel methods, the support vector machines and things like that. The completely radical revolution in machine learning. And they were very effective for a very long time. Along the way came the ensemble methods, random forest, XGBoost. Even today, now the new statement is, if you're dealing with tabular data, all you need to know is XGBoost. It solves all problems, does very well, always outdoes everything else. Then came deep learning, deep neural networks. In many class of problems, they just say, all right, deep neural networks wipes out classical machine learning. I've heard many such statements from people. It says, why bother? Like, people have asked me, why bother teaching this course at all? The only thing you should teach is deep neural networks, the other course, right? Because this is all irrelevant, right? So don't get disheartened. It is not irrelevant. All the effort that you're putting in is not. In fact, it is a foundational theorem. It is the no free lunch theorem, right? And remember, theorems are forever. Your software goes through V1, V2, V3 versions, and there are bugs in it. But in mathematics, a theorem once proven is true for eternity. There is no version 2 of the theorem, ever. There is no version 2 of the Pythagoras theorem. It is a theorem, right? So in the same way, no free lunch theorem says that there is no algorithm that is always superior to another algorithm. For some domains, for some data sets, certain algorithms outperform other algorithms. But in different domains, other algorithms will outperform this, right? And we will go through this exercise. At one point, I'll have you compare the performance of many algorithms on a data set, a hard data set, and you will see what happens. So anyway, that's a digression. We'll leave that. So remember that you have every algorithm is a hypothesis on what the data is. But only when you examine the data, you will know what the data is. The data will speak. It will have its story to tell. And the difference between your hypothesis and what the underlying ground truth is will show up in the prediction accuracies and other indicators, empirical indicators that will show up. Anyway, so that is the answer to that question. Now, anything else about discriminant analysis? Yeah, one more thing. In the discriminant analysis, there's a technical point. If we assume, the center of gravities are separated out, but if we assume that the shape of the hills is identical, they're identically distributed, the cows and ducks, in the feature space, then you end up with a linear decision boundary. I gave this very intuitive picture, just a pour sand from two bottles near each other, right? And when you will see two hills of sand, but forgetting the z-axis, the height axis, if you look at the line, it will be a straight line cutting through them. The perpendicular, the perpendicular connecting the hills, the line that is the decision boundary is a straight one. Now do another experiment. Take sand and take something a little bit slipperier, so that when you pour sand, it falls like this. But when you pour that, it sort of flows and it has a much harder time forming a big hill. It flattens out, right? So it spreads out. So now the variance of the two hills are different. In such a case, just observe and you will see that the boundary between them is curved. It is curved towards the peakier, the hill with a smaller variance, right? Towards the sand hill. That's how it will look. Just do this experiment on your table, and this point will become pretty obvious. I wish I could do that. There's a bigger table forming, but then also I'll create a mess and we'll have to clean it up. But anyway, do it at home, right? With your kids, you'll have fun. So anyway, that was all about discriminant analysis and its review, right? What does discriminant analysis do? Because of one advantage of discriminant analysis is it very naturally extends to multi-class classification, right? Because if you connect suppose you have ducks and cows and tiger, you connect the center of gravities of the three things, you get a triangle. The perpendicular bisector of each of the sides of the triangle will still meet at a point, and it will divide the feature space into three regions very naturally. And so discriminant analysis very naturally extends to multi-class classification. With logistic regression, for example, that was hard because it would always make a binary classifier. So how do you extend it to multi-class? You have to build many, many models, one versus rest, and see, is the probability of a duck versus not being a duck higher than the probability of being a horse versus not being a horse? Then it's a duck, things like that. You have to reason through, but you have to build many models. In linear discriminant analysis, you have to build a single model and you're done. So this is it, guys. And that is all I have to say about discriminant analysis. Any questions? This is a review of last time. Any questions?
Yeah, Asif, I had a quick question. So when you're transforming the like if you go up to the cow and duck example again,
Okay.
Yeah. So when you're transforming it onto the x1 tilde coordinate system, what would the coordinates now be? Like, how are you quantifying those coordinates?
Think about it, just rotation. I think if you do coordinate geometry in high school, you remember that rotation and translation.
Yeah.
Just cosine. There is a theta, cosine theta, sine. You know that matrix, rotation matrix. That's it. So x1 tilde is x1 cosine theta minus x2 sine theta. And likewise, x2 tilde is x1 sine theta plus x2 cosine theta. Remember that equation. So it is pretty much a rotation equation. Plus there is a translation. It is a rotation and a translation. That's all.
Okay, got it. Thank you.
That's that.
Or do we multiply one, I mean, x1 or x2 with a discriminant so that you do a matrix transformation? Is that what we do?
Yeah. See, it's the same thing. See,
Okay.
this matrix, right, can be decomposed into a translation and a rotation.
Okay. Okay.
It is visually obvious. No? If you let me draw it out to you. See, what happens is, let me use a color that I haven't used, and I hope this thing cooperates. You see this point, right? This is the origin. Let me just call it origin O, and this is the new origin O tilde, right?
Okay.
They can't see the pointer now.
Oh, I don't know. It is just that you can see the pointer moving the big point. Okay. So what is happening is this goes here, isn't it? So just think of it. The coordinate system, which was like this here, has gone to like this here. How would you do that? First step you would do, step one is you would take this coordinate axis to this point. Right? You would do a translation from here to here. Would you agree? You just shift the y-axis to this. Once you have shifted the y-axis, you rotate the x-axis, rotate it to be parallel to that now. Rotate it over. You're getting right?
Okay.
That is it. And you also not only do that, you translate the y-axis, this thing also up here. So first what you do is you go here. So your axis will look like this. And now all you need to do is a theta rotation.
Okay.
That is why you say that it's a translation and a rotation, basically. And then when you put the two matrices, when you take the two together, it will become your transformation matrix. Yeah? And effectively, you're in search of that. Yeah? So all of these things, one advice that I'll give to all of you, see, this simple intuition, I don't know how it is. Sometimes when I read the books on this topic, it gets into very complicated mathematics. Right? It does a lot of matrix, this and that. They're trying to say the same thing, but they say it in a much more formal language. Whenever you see complicated mathematics, don't be intimidated by it. Just break it down into pieces, because ultimately what is being said will be something very simple geometrically. Think geometrically, ask what is it, and it will be something absolute common sense. Right? And that's all it is. All right, so with that, if that is done, any more questions in the review? If no more questions, we'll take, we have been speaking for an hour. It is end of review. One part of our theory is over. We'll go into clustering. So let's take how many minutes break? 5, 10? 10. Let's take a 10-minute break. We'll start by talking about pattern recognition. This is the new territory we are entering, what we call unsupervised learning, and I'll treat these as synonymous. See, folks, whenever there is data, if there are causative forces behind the data, then are you guys able to see me clearly? Remote people?
Yes.
Okay, I don't know how well I'm visible, but okay. It's not that my head is being chopped off or something like that. I'm clear, right? Okay.
Yes,
So
fine.
maybe a little bit, yeah. All right. So whenever you have data and the data has some reason, some cause that produced it, generative forces, one of the things you may observe very often is that there is a pattern in the data. Are we together? Data has pattern. It is you expect patterns to be there. Let's say, so this is illustrated actually in a very common example. Suppose you take lots and lots of data, and let's imagine that those data sets are all two-dimensional. Like for whatever reason, all sorts of data, wind and pressure, this and that, whatever it is. And you gather the data. And if I were to ask you, how often are you likely to see any pattern in the data? How would you answer that? Like there are lots of data that have no pattern. For example, a white noise has no pattern, right? If you have sand completely smoothed out, then if you take a picture of it in the location of every grain of sand, you project it as a location that may not have a pattern. There are many, many situations where you don't have a pattern, but there are situations that you do have pattern in data. So if you were to ask this question, how likely are you to find pattern in data? How would you answer it? What proportion of the time? Like now, this is for the new students to answer only. What proportion of the time would you say that there are patterns in the data?
80%.
80%. That is a fairly good guess. Anyone else would like to venture? What about you?
More than 50%.
More than 50%. And you? How much would you say, Dhwani? 60% of the time you would see data. Any one of you who are attending the class for the first time, would you like to give a different answer? Sanjeev, here? Deshpande? Make a guess. It's all a guess. You don't know.
What's the question?
Are you attending it for the first time?
Yeah.
Yeah, okay. Make a guess.
My feeling is that data always should have 100% of the time should have some pattern.
Some pattern? No, we just took an example when it wouldn't, right? Smooth sand, smooth it. So may not, but
So we need to take out the noise. If data minus white noise, then
yeah.
should always have that.
Yeah, that is one answer. Yes, let's see what turns out. Yeah, but it's a good guess, and you have justified it well. Premjit, you're also attending it for the first time. How often do you see just noise, or how often do you see pattern in data? Generally, if you were given random sets of data.
It all depends on the context, right? The context that I
You take the universe of all data sets, all from all sorts of domains and measurements.
maybe about say 30 to 40%.
30-40%. Yeah, Sanjeev Deshpande, what's your guess?
20%.
20%. Sanjeev Kumar, what's your guess?
Well, I'm just maybe about 60%. And so
It's all right. So is there anyone else who would like to throw in a guess? A new student. So we have guesses. See, it is all over the place and it doesn't occur. Now I'll give you intuition that might help in this. See, data is empirical data. It's a measurement of something that happened, right? Behind something happening, there are causes. Quite often, whenever there are causes, those forces, they leave their signatures. And those signatures almost invariably leads to pattern. In fact, the most remarkable thing is when there is no pattern in the data, then something is at work wiping out the patterns, right? I'll give you an example. People often used to say that when you turn on the TV and it is not receiving any signal, your antenna is just picking up random noise, molecular agitation noise of the air or something like that. Little bits of electromagnetic agitations is picking up, right? And when you turn on the TV, do you remember that it used to be noise? Do you remember those days? Right? It used to be just noise that would come up if you're not tuned to a channel. And it turned out that too was not noise. What did it turn out to be? Come again?
The universal Big Bang noise.
Yes, Abhishek says universal Big Bang noise. Yes, indeed. Buried in there was a pattern. It was actually, we were hearing, metaphorically speaking, we were literally seeing the reverberations or the echoes of the Big Bang still reverberating through the universe in the cosmic microwave background. right? So, and that was a tremendous discovery and of vital importance.
Amplifier is turned off.
Oh, is it turned off? Or maybe it has run out of battery. It is on, but it is out of battery. Give me a second, guys. Sorry for the interruption. Let's try now. Once again, a bad battery. So I need to throw this. Give me a second, guys. I'll pause the recording for a moment, please. Generally, it's very hard to produce pure noise. We know in computer science, it's extremely hard to produce truly random numbers. We keep trying it. We create all sorts of pseudo random number generators. And we always have a sneaky feeling that there is a pattern still hiding in there. Very hard to produce true white noise. You can come close to it, but there may be a pattern still hiding in there. So pattern is sort of the norm. So like Abhishek said, it's almost always there. In one of the TV shows I used to like, and old TV shows, which is about mathematics, it is literally called Numbers. There are two brothers. One is a mathematical genius, a younger brother, and the elder brother is a FBI agent solving murders. In one of the first episodes, there was a demonstration that went like this. Well, there was always a bad guy who was murdering or doing terrible things. And the thing is, where is he? And FBI, they could not find a pattern in what he was doing, literally. And all the crime theories are based on the fact that the bad guys always have a pattern, right? You can find some way that they can do it. And the elder brother said, the FBI fellow said that there is no pattern here. And the younger brother, his first reaction was that it cannot be. If there is no pattern, somebody is deliberately trying to wipe their trace. They're deliberately randomizing or doing something like that. And then he comes up with a model of how, nonetheless, you can find some underlying pattern, some way of separating them out. And along the way, he does a very interesting demonstration, which I invite you to do in your mind. He says that for every person, enter into the room. I mean, I will change it. I won't do exactly the same demonstration, but something equivalent. If you just send people and ask them to stand just about wherever they want, right? One person at a time. And wherever you stand, just take an invisible marker and put a mark on the floor and then walk out. Then when everybody has done and you shine the light into the room, you will actually see, this is different from the one in the TV show, but you'll actually see that those locations are clustered. Similarly, if you just ask people to enter a room in which they are already standing, and say, go stand somewhere, either they will deliberately try to stand apart, right? Because they're consciously trying to spread out, right? Or that is a conscious effort not to have a pattern. Or if you just leave them alone in a social gathering, what happens? People form groups, they form clusters. So clusters, patterns, they are everywhere, right? And they're there unless you put in an effort for it not to be there. Most often there's some pattern. So now the question comes, in machine learning, what is the value of pattern recognition? Right? What is the learning? Or why should we care? Yes.
Just want to add I missed a little bit to get support for call. So although there is pattern in the data, the rider I wanted to add there is, by the time the data gets to a person who wants to look at it, multiple things have overlap. And after that, it's hard to discern the pattern.
That could be true. That is one possibility. What Premjit is saying is there may be a pattern in the data, but by the time you get it, reality has changed and other things have happened. Those could happen. They are always confounding factors. They are always things that complicate things. But nonetheless, the pattern is there, right? In anything you look at, there will be pattern, right? It may not be the same pattern that you initially it had. Now it may have a different pattern, but it will still have a pattern to it. Right? And so there will be layers of meaning, layers of patterns sitting in something, or changing patterns sitting in something. So for example, if you live in the desert, you literally can see the sand dunes every time there's a storm, right? There is a wind. the sand dunes change shape. The pattern changes. With time, the patterns change. So it is there, that's true. All right, so with that, I'll ask this question. What is the value, basically, of pattern recognition? Why should we do that? So again, we're talking a very high level generality. So let's actually go up in a balloon, go up to a high level, to a height. See, suppose you were, take this example and do this thought experiment. My professor used to, I think, use the word Gedanken experiment. This is German for thought experiment. So let's do that, Gedanken experiment. What you do is you are, I hope I pronounced that word right. You go into the city of San Francisco. You don't have a map. Forget that you have Google Maps, right? You are trying to get your bearings. You are on the Market Street in San Francisco, and then you're trying to find the location of some restaurant or something, and you're wandering around. And what happens is that as you wander around, gradually you begin to get a sense of your local bearings, that this is perpendicular to that, and for food I need to go here, and so forth. You have some local understanding of what the lay of the land is locally. But what happens if you suddenly got into a hot air balloon over the and rose above the city? What will it do to your understanding? In one glance, I hope you would agree that you would literally see the peninsula, you would see the financial district, you would see the park, San Francisco, Golden Gate Park, you would see where the beach is, you would see where the residential houses are, and you would get a much better intuition so that next time you're back into the city, even if you don't have directions, you would have a general sense with a compass which direction to go. Right? If you're looking for shopping areas, which direction to go. Would you agree with that? Right? So finding patterns is tremendously useful, and it is a learning in itself. The discovery of patterns is of vital importance. So the techniques that we are going to deal with today, there are two, there are many techniques that we'll talk about. Two of them, one I just mentioned a little while ago, which was dimensionality reduction. You notice that data can actually be, to the first approximation, considered to be living in a lower dimensional space. That's a big topic. We'll do it much more thoroughly later on. Today, we won't be able to do justice. But the second thing is we notice that in data, there are clusters. For example, if you rise up above San Francisco, so let me try to make an example of San Francisco. Let's say that this is the bay, right? And this is this is a terrible picture of the bay, but I will try to do a better job. And the sea, why am I not able to do that? Okay, so let's say that this is, and this here is, with this big pointer is getting hard for me to erase things. Okay, and this is the Golden Gate Bridge. And for those of you who haven't been to San Francisco area, Bay Area, I apologize, but just see that this is land. Let me just mark the land with some very land-like color. Okay, let me instead mark the water. This is water. And everything else is land. This is the bay. This is the Pacific Ocean. The Pacific Ocean. This is San Francisco. In the San Francisco, you notice that there is this region, which is, I'll call it like this. This is the financial district, financial and commercial district.
Market Street.
Yes, Market Street, basically.
And across the bridge is Marin County.
Yes, and this is Marin County. Let's say here, Marin County. Marin County. But yeah, so this is San Francisco. Well, this is not whole San Francisco. That would be inaccurate, but this is close to it. Let's say this is SF area. Now in this, there is a green belt, which again, I'll exaggerate and put it like this. The green belt, and then there is the housing belt. The housing approximately looks like this. It spreads out. What is it? Daly City and all the housing areas and so on and so and the other places. Is that a reasonable approximation?
Yeah, that's South San Francisco. And
yeah. all of
The
that.
industrial area.
And then the industrial area again starts. So then there is another industrial area that starts here. Yellow is the industrial area. So what do you see? Do you see that? Do you see a clustering of similar things? A cluster for the trees, which is the Golden Gate Park. A cluster for houses which have tilted roofs. Then buildings with tilted residential houses, and a clustering of this flat-roofed commercial district. You can, and high-rise buildings. You see, they exist in clusters. In fact, most of the iconic pictures of big cities like Chicago, like New York, near San Francisco, and so forth, all you see is clusters of high-rise, isn't it? The skyline is clusters of high-rise. So clusters are everywhere. So we will learn techniques of clustering, because to know this is, in a way, you can say you learn something about San Francisco, the city of San Francisco, right? That is the purpose of clustering. Now, a clustering of data is also inherent. We were talking of cows and ducks. Now, when we go back and look at it, what do you see here? In this data, you see clusters, isn't it? All the ducks are clustered at one place in the one region of the feature space. All the cows are clustered in another region of the feature space. Are we together, right? And when you generalize it to three, you cows, ducks, and horses, once again, or tigers, once again, there are three clusters. So clusters are there. They may be approximate, or they may be very clearly discernible clusters, right? So we will search for clustering. Now, how do we search for clusters in data? So one of the things is, see, so we will go with clustering today, clusters.